right, so what we've been discussing thus far is lots of different integration techniques, and we've been looking at different strategies. And if I was to give you a problem that says, what is the integration of sine 2x? One strategy we can do here is we can naturally do a quick u subset, u equal to 2x, not a big deal. You can also use that double angle identity. You can take it, you can express it as 2 sine of x cosine of x, and then do a u sub not on the 2x, but a u sub on the sine. So there's different ways of how I can approach this problem. And we also looked at what if it's going to take this and crank it up a little bit more and say sine squared of x cosine cubed. And we looked at the mechanics behind this. And as we kept looking at these more and more and more, we got to more interesting techniques. And if I even had the integration of dx x cubed plus 1, I can crank this thing out. I could do a partial fraction decomposition. I know the identity for the sum of cubes. If I have a cubed plus b cubed, that's a plus b, a squared, flip the sign, ab, b squared. And then I can decouple it, I can apply this identity, and I can look at it in terms of partial fractions. Okay, we got that. It's not too big of an issue. So what if I was to give you a problem now that looked at the integration of not just sine, but sine of x squared. And I integrate from 0 to 1. Okay, how am I going to solve this problem? Well, again, I look at my checklist and I ask myself, can I do a quick u sub on it? And I'm saying, no, I can't do a quick u sub on it. And then I say, okay, does integration by parts work? And I say, well, I don't really see much of a product up here that's causing me some kind of snag. So you move on to the next thing. I don't see a partial fractions problem, at least nothing that's very evident. Usually when I see irrational functions, there's some identities I can use to change it into a rational function if I need to, but nothing like that's really come in suit here. And I probably don't want to do a trigonometric substitution on a trig integral. That's nasty. You can do it. It just makes it really crazy. So I'm kind of at an impasse. How am I going to integrate this given problem? We'll take it back. When we're first thinking about integration, we integrate a function, f of x dx. One of the applications was if I looked at the function and calculate the area under the curve, that would correspond to my integration. And recall how we actually got it all started, how we actually constructed the integral. Once again, we can pack it full with a bunch of circles. That will work, but it's going to be very cumbersome, very complex, and start figuring out what all the circles I need. So we said, let's make this more systematic. Let's make this more mechanical, so there's less thought involved in trying to figure everything out, so it's easier to go through. And we said, okay, let's use this process known as Riemann sums. We're looking at the area of each one of these rectangles, and I'm taking it and pulling it all together. And we say, okay, we'll sum up all the areas. F of x corresponds to the height, and then dx would correspond to the width. You have some kind of point up here you plug in, and you might have a case starting off at 1 and going to the value of n. So you can talk about what's called either the right-hand rule or left-hand rule. But again, this is an approximation. So you would keep refining the approximation, make it better and better and better. And as you continuously keep refining approximation, that invokes the whole entire idea of a limit, and you would turn your approximation into exact. Well, that was the whole entire idea behind this of integration. Small parts, once again, come together to form the larger picture. But what I want to do is, guys, I want to think more like an engineer, more like a scientist. And I see that this works, but it's slow and it's clunky. I want to make this better. And the idea, again, is to use congruent shapes that better fit the curve. See, if I use shapes that better fit the curve, I get to the answer a whole lot faster using a bunch of these circles or triangles. So a shape that would better fit the curve, yes, I can definitely use a bunch of rectangles, but I have a bunch of over approximation. I have a bunch of under approximation. So to fit the curve better, why not make a beeline and go right there? And look at that object. Then why not make another beeline and look at that object? And then also that one. So you cut out the fat, so to say. So there's less under approximation and less over approximation. But the shapes that I have now, they're no longer rectangles. What do I have? I got a bunch of trapezoids. And the idea behind integration is I add the small parts together to form the larger picture. So what I want to do is I want to add up this trapezoid, trapezoid 1, trapezoid 2, trapezoid 3, figure out its area, add them all up to get my approximation. Okay, well that's my idea. Let's see if we can actually put it all together now. Well, the first thing is this. What's the area of a trapezoid? Well, the first thing again is I want to take the region from A to B. I want to chop it up. In order to make it easy, I want to make it equally spaced. So the distance from here to here to here is all the same. And I'll call it delta x again. That worked really well last time. Let's do it once again. Delta x is going to correspond to b minus a. In b minus a, this is going to be the length of the whole entire interval. And I'm going to chop it up into n equal pieces, into n partitions. Well, if I do that, I'm going to also go back to the notation where we had x naught. And x naught is the very first value. Then I'd move over to this value right here. That'd be x1. And then the next one, x2, then the next one, x3, and then so on and so forth, till I get down to this kth one, wherever I'm looking at. So if I want to go to x1, how far away is x1 from x0? That's 1 delta x. So I would take whatever I had beforehand and add 1 delta x to it. And if I want to go from here to there, how far did I travel? 2 of these. So I would have a plus 2 delta x. If I want to go to the third one, x3, I'm going to go 1, 2, and then 3 delta x's. What's the pattern? Look at the index. Look how many delta x's you're doing. So I can take this whole entire thing, I can collapse it down, and it gives me a really nice formula. It says x of k is going to be nothing more than the very first term, a plus delta x. Okay, so I took everything and packaged it up nice and tidy in this nice little identity. Well, that still begs the question, how do I calculate the area of the trapezoid? So if this is the x of k value, this value up here, that's a vertical measurement, and we always measure vertically by that y. This is f evaluated at x of k. And then if I want to go from up to here, that's also another vertical measurement. It's not horizontal like x is. If you've forgotten what the area of a trapezoid is, not a big deal. If you were to draw a line through, what you would find is you have a rectangle, and then you got a right triangle. Put the two pieces together. Here's the area of the rectangle. Now, first off, if I go from x of k to x of k plus 1, this distance is called delta x. So you have f of x k delta x plus Well, the area of the triangle is going to be the base, delta x, times the height. And what's the height of this? That's going to be the discrepancy, taking the whole entire height, chopping that piece off right there. So this part is the height minus that. And then divide it all by 2. So here is your area of the rectangle part. And here is the area of the triangle part. Simplify it down a little bit more. Or, again, you could just simply remember what the formula is for a trapezoid, where you would have your base 1, base 2, you have your base 1 plus your base 2, multiply by where that height is, or divided by 2. You can take this and topple it over, and maybe you're more accustomed to seeing it more like this. So there it is. There's the formula to find the area of one trapezoid. But I got a lot of trapezoids right here. I'm going to have to start integrating them all together to figure out what's going to happen. So let's do it. Trapezoid 1, trapezoid 2, 3, and trapezoid 4. Take trapezoid 1, add trapezoid 2, 3, and 4. Calculate the corresponding areas. So here again, this is going to be x of naught, x1, x2, x3, and the next 4. I see that I'm going to have 4 partitions, at least in this particular case, this illustration. If I want to find the area, I know the area formula. That's going to be delta x over 2. And I'm going to have f of x of 0, x naught, then f of x1. Then I'll have delta x over 2. And then the next one, I'm going to have x sub 1, and then x sub 2. And then I'm going to do it again. Delta x over 2, f of x2, f of x3. And then for the last one. So this is the area for trapezoid 1. This is the area for trapezoid 2, trapezoid 3, trapezoid 4. Now, just like we were working with Riemann sums, the left-hand rule, right-hand rule, it's starting to get a little bit cumbersome here. So I might want to simplify it down a little bit more. And the first thing I note here is this. They all have a delta x in it. You can factor that piece out. And when you factor that out, guys, what's left? This part. But look at this. That as well. You have 2 copies of them. And look at this. You also have 2 copies. And look at this. You also have 2 copies. And the last one, you don't have, just a single copy. So here, if I start integrating all my trapezoids together, I get this nice rule right here. It's a little different from the Riemann sums we've been working with earlier, which should be the case because we're using different shapes and just looking at rectangles. And what I have here is something called the trapezoidal rule. Why do I have 2 copies of these, by the way? I'm using this side twice. One side is used for this trapezoid, and this side is used for this trapezoid. It's just this side right here is only used once. Whenever analytical procedures, when they fail, when I can't do a quick use of, I can't do an integration of my parts, partial fractions is out the window, the last hope you got here is to go about it numerically. And instead of using left hand, right hand, I can go ahead and look at trapezoids which better fit the curve, which would presumably say that I'm going to get to the answer a whole lot faster. Again, I can't do this analytically. It's impossible. So I'm going to have to resort to a numerical process to get the best case here. And let's say that we're going to be looking at 4 partitions. If you guys have a calculator, this would be a good time to take it out. You're going to need it here in a moment. So the first thing I want to do here is I want to go ahead and just calculate what is my delta x. Well, delta x again is going to be b minus a over n. But the problem is, tell me what b was. You didn't say b equals. Where am I going to find b equals? It's right there. It's the upper bound. The lower bound is going to be what your a is. So take it, plug it in. And here you're going to have to be given some kind of partition. Otherwise, you're going to have some problems here actually doing a numerical approximation. So we see our spread is going to be a quarter. So delta x is going to be 1/4. And the next thing I want to do is I just want to see what's going to happen here with my individual x terms. My x0, x1, 2, 3, and 4. The very first one is where you start off at. That's going to have to be your a. The very last term is where you stop at. That's going to have to be your b. If these are misaligned, there's some kind of problem, go back and check it out. So if I start off at 0, and I want to go 1 over, get to the next one, I want a distance of a quarter. Then you're going to go another one over here. So you'd say 0 plus 2 times a fourth. And then you want to go to the next one. That's going to be 0 plus 3 times a fourth. And then to the next one. 0 plus 4 times a fourth. So in other words, I'm going to have 2/4, or I'm going to have a half, 3/4, and then 4/4, 1. Okay, so after you figure out your x values, you have all these values now. What you're going to do next is just do the function evaluation at these particular values. Okay, so I'm going to give you a moment here, see what you're going to get for these values. You're going to have to plug these into your calculator to figure these things out. Except for this one. What's that? If it's 0 and you plug 0 into the sign of x squared, you get 0. Okay, that's nice. See what you get for the next 4. And this kind of brings up the question, how many significant digits do you need? Well, if you do not enough, it's going to have a lot of error in the calculation eventually. Probably a good 3 or 4 might be sufficient. All right, now look at the formula. You figured out the x0, the x1, x2, all the x values. You did the function evaluation. What comes next? Take your pieces in between, multiply it all by 2. And then after you do that calculation, what comes next? So add them all up. You get the thing on the inside set of parentheses, 2.527836. Okay, now next thing is I do have my delta x, dividing it by 2. Delta x was a quarter, so this becomes an eighth. Multiply it by 2.5278036. And when you do that, you get approximately 0.31597,545. So we can't do this analytically, but we got kind of a good answer numerically, whatever good means. You could do all this, Calculus 2, in a Microsoft Excel spreadsheet. Figure out what's happened with the x values, and then do the function evaluation, and then multiply everything by 2. It's kind of a little spreadsheet feel up here, if you notice. Now, we can do this analytically. We know what's going to happen, but let's go ahead and practice it numerically. What would be a good approximation if I was going to go about using the trapezoidal rule? If I was to look at the graph, 1 over x squared plus 1, how would I graph this? What would happen if x is 0? If x is 0, take it and plug it in. You're right there. Then what would happen if time continue ticking on. Go to 1, then 2, then 3. What happens as x goes off towards positive infinity? What's happening to your function? It's going down to 0. And likewise that way. I got a bell curve. Look at that. All right, so I'm looking from 0 to 1. I want to calculate this area, and I want to use the trapezoid rule to go about this procedure. The first thing is figure out your delta x. Figure out that spread. B minus A over N. And B is going to be 1. A is going to be 0. Take it, plug it all in. And what you get here is you get a fifth. Okay, that's fantastic. So what's x naught? What's x1? x2? All right, after you figure out the x values, calculate the function values. Now, here's a question. How could you do this very quickly without using a calculator if you had to do the evaluation? Well, first off, this is 0. If you take 0, plug it in, you're going to get 1. And if you plugged in 1 right here, you can get a half. Those aren't the issues. The issue is what happens here for these 4. Think like a scientist. Think like an engineer. You can keep doing the same thing over and over and over again until you get so tired you just don't want to do it anymore. So you can work smarter or you can work harder. Which way do you prefer? I'd rather work a little smarter about it. I don't want to work a really long time on these problems. So when I plug things in, what am I plugging in? I'm plugging in these fractions. Every single one is a fraction. Now, my scientific mind starts thinking, okay, I want to do it all at once. I don't want to do it 4 times. So if I'm going to do it all at once, I'm going to have to create myself a formula. And I know that all these are going to be 1 over 5. They're going to have this formula P over Q whenever we plug it in. So if I do it like this is actually going to speed up a lot of time in my calculations, especially if I was going to have like 10 calculations to do or 20 calculations to do. I don't want to do one after the other after the other. That's a time sink. This will save you a lot of time. Simplify it down, and there it is. In this particular case, what we're going to have here is Q is going to correspond to a fifth. Because we're looking at a fifth, 2/5, 3/5, 4/5. So every single one of these fractions is going to have a 25 up top. Then you're going to have a slight variation down here in the denominator. So here's my question. Would you prefer to take a fifth, plug it into the function, then take 2/5, plug it into your function, or would you prefer to just do it once and for all? I prefer this route. It's easier. Okay, so what we're going to have here is 25 over 26. 25, take 2, square it. We're going to have 29. Take 3, square it. Take 4, square it. 16, 25, 30. After you do the evaluations of the function, multiply everything by 2. And notice here in this case, this is the exact value. I didn't do any approximations, so my answer is exact so far. Whenever I start doing approximations, that's where things get a little funny. You multiply everything by 2. And after you multiply everything by 2, add everything up. Now, if you were to add everything up, this is what you're going to come up with. Multiply it by delta x over 2. Delta x was 1/5. So this part now becomes 1/10. So you get approximately 0.783746. So the question is, yeah, that's a numerical approximation to the answer. How good is it though? How accurate is it? Well, that's a question we're going to have to kind of wait to explore, but any questions about this procedure? I guess first question is, do I need to know this formula? Yeah, you're going to need to know this formula up here, the trapezoidal rule. Okay, so make sure you do know this. All right, guys, we're out of time. I'll see you next time. You guys have a great day.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.